Okay, good afternoon. Hope everybody enjoyed the break and lunch, or maybe had a coffee, so did not fall asleep. Now in our session we will have 4 interesting talks. We start with 2 symposium talks, both from the University of Stuttgart, from different institutions, as I've seen on all the acronyms. And we start with the first one with Pascal Hirmer, partial execution of ledger plans during modeling time. It's 2 talks, 30 minutes each. Afterwards we have a break, and then we have some tutorials on health and on services. Okay.
Thank you very much for the introduction. So the most important things have already been said. My name is Pascal Hirmer, and I'm going to talk about partial execution of Mashup plans during modeling time. I think most of you will think, what are Mashup plans? This mystery will be solved very soon in this presentation. It's joint work with my colleague Michael from the same institute, and I'm in the group with Professor Mitchell as a PhD student. As you can see on the left side, it's about big data. So we've heard a lot about big data, for example, from Daniela yesterday or today from Harald Schönig. So I don't have to go into details what are the issues of big data, but I will start with a quick motivation of the overall issues. So as you all know, there's an increasing amount of data, and data sources are, of course, heterogeneous, they are very distributed, and they are dynamic, which means they change very often. So coping with this complexity is called coping with the big data problem. And we've heard about these 3 V's of big data, and of 5 V's and 7 V's, so it's very complex. But the overall question is, how can we extract important information from a large amount of heterogeneous distributed data? In my PhD, I'm working on an approach to cope with this issue, and it's called the FlexMesh approach. And it's about flexible modeling and execution of data integration and processing driven by user requirements. So I won't go into details of my PhD thesis, of course, because it will take a lot of time, I guess. So if you are interested in this, after the talk, you can ask me details at the poster session. So how does FlexMesh work? First of all, there is a Mashup modeler. So maybe some of you have heard about data mashups. It's basically very similar to ETL tools. What do I want to do? I want to define data sources, and I want to define how data should be processed, filtered, analyzed, and so on, based on a graphical model. This graphical model is called Mashup plan in the FlexMesh approach. Let's go into details. So as you can see in the Mashup plan on the right, so this one, there are data sources and data operations. Data sources represent, for example, databases, unstructured text documents, and so on. Any kind of data source. Data operations can also be very heterogeneous. It could be a filter, for example, an aggregation operation, but also, of course, more sophisticated things such as analytics like classification, clustering, and so on. So the idea of this model is that we can plug all these components together in an arbitrary manner. So I can connect arbitrary data sources with data operations, and in the end I get the result that I want. So in this example, one could imagine that I have like an SQL database over here. I want to filter the data and aggregate it with data from another data store and put it into an intermediate storage. Then I could split the data, and I could run some analysis or visualization. So there are a lot of use cases for that. The things on the left is not that important, so I focus on domain experts. So for me it's very important that people can model these Mashup plans without any specific technical knowledge about analytics algorithms and so on. So it should be kept as simple as possible, which is not that relevant for this. And an IT expert is responsible for creating these nodes in the Mashup. Of course, we want to compose data operations using these Mashup plans, and what comes to mind are services. right? So each node in this Mashup plan is associated with a service, which is either responsible for extraction when we model a data source, or for data processing or analytics when we model a data operation. So all these nodes are represented by services that are called in the order as defined in the Mashup. So that's very important for this. Okay, once the user created the Mashup plan, he received this pipes and filters based model, and he can select requirements for the execution of this Mashup plan. I will skip this. If you're interested in this, you can talk to me at the poster session. After that, this Mashup plan is transformed into something executable. Right? This is only a graphical pipes and filters model. You can't execute it. And what I do is I transform it into a workflow, which then calls corresponding services that extract and process the data. So it's actually quite simple. So the whole FlexMesh model is of course more complex, but that's the stuff we need to understand the concepts of this paper. So creation of the Mashup plan, and then execution and transformation into a workflow model and execution in a corresponding engine. That's what the current old version of the tool looks like. So you can model like data sources. So imagine you have 2 hospitals. They contain patient data. One hospital data should be filtered according to, I don't know, patient's age, for example. I want to merge the data, analyze it, store the results, and visualize. So this would be a common use case. And of course, there are many operations, and each of these operations are corresponded to one or more services. So now let's come to the motivation of this paper. So this was FlexMesh, it's already there. That's what I said. FlexMesh processes data based on workflows that are invoking data processing services. However, Mashup plans are transformed as a whole into executable workflows. So that's a problem. Sometimes I model like scenarios with very large amounts of data, and I press on transform and run, then transform the Mashup plan, and it runs the bootloader. And for the large amount of data, this can take up to 2 hours. Okay, then I'm sitting there and waiting until it finishes. I can, of course, implement a progress bar, but yeah, that's not what the user wants. He wants to have his results as soon as possible. So also, when I change the Mashup plan slightly, so if I have a, if I want to get the results in an explorative manner by just changing the model as until I get the results I want, then I have to re-execute the whole Mashup plan again. So for one minor parameter change, I have to execute everything again, and that's a problem. So this leads to high efficiency issues, and also currently there are no possibilities to show an immediate results. So maybe I first want to analyze something, I want to look at the results, and then I want to do some more steps with this data. Currently, I have to run the whole thing, look at the results, and then see how I can change the model. So the goal of this paper was, why don't we just partially execute this Mashup plan during the modeling time? Because the modeler needs time to create these models. And this time can be used to run the data operations in the background. And this also has the advantage that he can show intermediate results during modeling, which is very helpful for the users. And it's not really increasing the efficiency. I thought about it, but it's wrong to say it's more efficient, because it takes the same time for processing the data, of course. But if we do it during modeling time, then we can use this time, and it's a felt faster execution for the model. Because once he clicks, after modeling the whole graph, once he clicks on execution, it takes a very short time, right? Because most of the model has already been processed in the backend. So those are the contributions. We want to transform and execute not the whole Mashup plan, but single nodes. We want to show states of execution during modeling, so we know that nodes are currently being processed or that they are done processing, and we want to show intermediate results. And this is the first step for partial execution. There are, of course, a lot of other features which we will see in the future work section in the end. However, there are challenges, right? Data becomes stale. When I create the whole model, I transform it, and then I run it. Then I'm working on the current data sets, right? If I have data that changes very often and I execute some data operations during modeling, so before the model is finished, then data can become stale, right? Then the final results can become wrong or can't be used anymore. So that's an issue we have to cope with. We have to cope with constant changes in the Mashup plan. So if the user changes a lot, then we have to transform a lot of nodes. We have to execute a lot of nodes. So that's very difficult. And also there are dependencies in the model. I can't just execute any node I want because one node might depend on the other. And of course, I think most of you know the work of Mirko Sonntag, who worked on the model as you go approach, which is also his PhD thesis. And of course, it's very similar to that. Sure. Mirko was actually the inspiration for this work when he did his PhD thesis presentation in 2016. And also, this is also related work I want to mention. It's from Bertrand Ludescher, who also does something very similar with his smart workflow reruns. So this is inspiration for this work. I took these concepts, of course, and I applied them to Mashup plans, so that's a higher abstraction on top of workflows. And furthermore, what is also different is that we enable implicit execution. So during the user models, we implicitly execute the node C models, and in the other approaches, you have to explicitly say, okay, you have to run this, this part of the flow right now. So, yeah. Okay, let's come to the main approach. Let's take a look at the challenges. That's what I mentioned 2 slides before. And from these challenges, we derived some requirements for the approach. Okay, we need some kind of data expiration time. Data becomes stale, so if I start modeling and I extract data from a MySQL database and I filter it and I store the intermediate results, and then I keep modeling for an hour, then maybe the data in the SQL data store is stale because new data has come, and in the ages of sensors and IoT this happens a lot, right? So we need some means to define how can we define the lifetime of data. Yeah, we have to reduce the staleness of data. We have to check for dependencies in the Mashup plan, so which nodes can be executed and which nodes can't be executed. And of course, we have to split this Mashup plan somehow into fragments and transform these single fragments into workflow fragments that then execute the services that process the data. We need a persistent storage of intermediate results, which should also be some kind of efficient and can store a lot of data. And we need some feedback for the user so we can see intermediate results. Okay, so we came up with this architecture, and the white boxes is the old flex mesh approach. On top there's a modeling layer, and in the old approach we just transformed everything that was modeled on top. We execute it in a workflow engine, and that's it. Now there's a new layer, which is the partial execution coordination layer. There's an interface that communicates with the front end. There's a component that can check for dependencies in the model. There's a data refresher that handles status of data. And there's the main component, the partial executor, that handles the nodes being partially executed in the Mashup. And of course, there's an intermediate storage for the intermediate results. Or one could also call it storage. Okay, let's start with a simple example. I think this summarizes what I just said. So on the bottom, we kind of have the architecture again. And let's have a look at this example. So for example, I model a MySQL database and there's patient data in it. And I want to extract the table patients. So once I'm finished modeling and configuring this node, so for example with the IP of the database and the password and username, then it is handed over to the partial executor, and it extracts the data from the database by calling the service and stores it into the intermediate storage. So now I want to continue modeling. So as a user, I don't see this, of course. I want to apply a filter where the age of the patient is larger than 50. So of course, I can also execute this filter. I don't have to extract the data again because it's already in the intermediate storage. So it's handed to the partially executed component. This data is used as input for the workflow engine. So we transform this filter node into an executable workflow fragment. It gets the input data from this extract operation as input and executes this node. So after that, the results are of course again stored in the intermediate storage. And so on. So, but this is an issue. So now I want to have a join with another data source. So I hand the join over and I understand, okay, I can't do anything without it because the join needs 2 inputs. And the second input is not there. So this is a typical dependency. I can't execute this node. But once I model a second data source and I expect data from it, for example, in this time the table is called patient_data, then I can finally join the data, and this information is already in the partially executed component that the join should be executed once it is possible. We will see that in the next slides how this can be done. Okay, it gets the data and it executes. And this can of course then also be done for following nodes in the mesh. So that's the example we saw in the screenshot before. Now I want to talk a bit about the components. So what did we have to do to achieve this functionality? First of all, we had to improve the modeling layer of FlexMesh, so the modeling of the Mashup layer. First of all, we implemented a means to show the current state of execution of a node. So as you saw in the screenshot, all nodes were white. So in the new approach, this means it has been recently placed and nothing has been done yet with this node. If it is red, then it's not properly configured, so we can't run it. It's outdated because data became stale, or there was an error during execution. If it's yellow, then it's ready to process, or it's currently in execution. And as you can see, we are also able to show like the current state of execution. Of course, this also depends on the implementation of the services. So I have to get this information from the service itself, right? I have a service that expects data from like a MySQL database, for example, and the service has to give me the progress information. So if I don't have it, I can't show it. And if it's green, it's completed, and I can have a look at intermediate results. Also, we implemented a way to show intermediate results during modeling time. This is very easily done because currently we only show raw data, and my colleague is working on visualizations of data, so in the future he will find a way to visualize it in a nice way. Yeah, you can, that's already been said, you can implicitly execute the Mashup plan instead of manual treatment. And furthermore, there's now a means to define lifetime of data in the data source nodes of the plan. Of course, this is very difficult, and most of the reviewers says that it's not easy to define it. That's also part of future work to figure that properly out. So luckily there were also some good hints in the review comments, so in the future we will think about that more deeply. And the state of execution is also stored in the partially executed mode. And then there's the modeling interface communicator, which serves as interface between the Mashup modeling and the partial execution layer, and it handles all the communication. So it delivers intermediate results to show in the front end. It offers information about the current state of execution, so we can show them in the nodes we've seen before. And it coordinates all components, so it's the main coordination component. Okay. Now there could, of course, also be dependencies in the Mashup plan. How do we cope with that? In the backend, there's the dependency check component, and it keeps a model of the whole Mashup plan all the time. It transforms this model into what we call a dependency graph. And a dependency graph is very simple. So it defines which nodes are currently depending on another node and whether they can be executed or not. So for example, we can't execute node 6 because it depends on 2, 1, 5, and 4. Right? We first have to execute 1, 2, 5, and 4, and also 3 to execute 6. Also, node 2 depends on the execution of node 1, and so on. So which nodes can we execute? The nodes without any outgoing actions. So we can execute 1 and we can execute 3. So this is very simple, of course. Yeah.
One question.
Yeah.
If you look at the dependency from 6 to 1, it's an indirect dependency through 2, right?
Yeah.
And you have noticed it's in detail there, but the one between 6 and 3 was this of the same.
I just saw it. It's a mistake in the slide. Okay. Yeah, the Mashup plan is transformed into this dependency graph, and it's constantly updated with the current state of the model. So the dependency graph can indicate which nodes we can execute and which nodes we can't. And then there's the main component, the partial executor component, which also stores the twin model of the Mashup plan, so it understands which nodes have currently been executed and which nodes haven't been executed. So we have the nodes, the edges, and the current state of execution. And it also contains information about the available intermediate results. So it coordinates the execution of parts of the Mashup plan, so it has to know which intermediate results are there, and so it can be fed to the workflow engine, and the corresponding workflow fragment can be executed. Yeah. The execution is triggered by the dependency checker. Once the dependency graph says, hey, you can execute a new node, then it sends it to the partial executor component, and it can start transforming and executing the node. Single nodes are executed in the workflow engine. In the future, we think about some subgraphs, not only single nodes, but in the first step, we only call single nodes, and available intermediate results can be used as input for the execution. That's what I just. Once the fragment is done executing in the engine, we store it in an intermediate storage over here, and we hand it to the front end to display the intermediate results. And the state of execution is stored and provided to the front end. So we can turn the nodes from yellow to green. So that's an unsolved issue, how to cope with re-execution of currently executed long-running services. I'm executing one node which runs a long time, then I change the parameterization of this node, and it has to be re-executed. Okay, what I'm doing now? It's long running. Should I abort the service execution? So should I abort the currently executed workflow and start over? But the results are lost, and it's long running, so it's not good, and it's also costly. Should I use the current execution? This leads to wrong results, because I have to re-execute this node because its parameterization has changed, or the underlying data has changed. So, I don't know, future work. Okay. Then the last component is the data refresher. The refresher, that's what I said in the beginning. Intermediate data becomes stale over time. So we need a means to define lifetime of data. For example, high-frequent sensor data leads to low lifetime. In general, it's an assumption. And non-frequent events maybe have a high lifetime. Maybe this would also be a very interesting work. I think there's also a lot of related work that figures out how fast data becomes stale. So maybe we will check that also out in the future. Currently, some expert defines the lifetime of data. Yeah, that's what I mentioned in some slides before. That's very different. And yeah, the idea of the data refresher is, so we have a lifetime of data in seconds, and once the data becomes stale, then we remove it from the intermediate storage, and we have to re-execute the corresponding service again. So we validated this based on our own requirements. So of course, it all works out fine. So how can we wanted to define a data expiration time? Okay, this can be done by experts. Okay, it's a bit fussy, but we realized that the reduction of status of data can be done by refreshing by this data refresher component. Dependency checks are solved through the dependency graphs. And splitting the Mashup plans into fragment was actually pretty easy because the transformation component could already handle this. So I could already take one node and say transform it into a workflow fragment and execute it. This was already possible, so we didn't have to do anything there. Persistent storage was solved by an intermediate storage. We'll see this in the implementation, which technologies we use. and user feedback is provided through the UI. So we cope with all the requirements we thought about before. The implementation is based on these technologies. On the top level, we have TypeScript and JS as a modeling framework. So we also implemented a new UI because the old UI couldn't cope with all the features we wanted. And the partial execution coordination layer is fully implemented in Java, and it uses the MongoDB as intermediate storage. And then there's the transformation layer. This was already there. It's Java code, which uses DeepL and WSDL. And our execution is done in an Apache ODE workflow based on Java Web Services. And this is the new UI. It's currently not open source, so everything is open source, but the new UI still is in progress. So at some point in time, it will also be open source, and you can download it from GitHub. So if you Google FlexMesh, it will be the first hit on GitHub, and you can check it out. Of course, it's also a research prototype, so you might need some help with setting it. Okay, let's come to the conclusions. What we did is we enabled partial execution of Mashup plans, showed intermediate results, and we reached a faster runtime of the meshes. Future work, I mentioned a lot of stuff during the presentation, but what we're currently working on is executing subgraphs and doing some user studies. Is this really helpful? So first do the research and then see if it really makes sense. Okay, do I still have 1 minute? That's perfect, because then I can do some advertisement for a workshop we are doing. It's a workshop at the PERCOM International Conference on Pervasive Computing, which is a very high-ranked conference, and it's all about context awareness. It's in Athens, and the paper submission deadline is on November the 11th. So if you are interested in context awareness, feel free to hand in papers or talk to me after the presentation in the coffee breaks. Okay, thank you very much.
Thank you. Yeah.
So I don't have a question, but possibly a remark. So I think should talk to each other related to your data refreshing issue. Because in our web caching approach, we use some kind of machine learning mechanism to kind of learn the times to live, by which we adjust expiration-based caches in the web.
Ah, that's good. Yeah.
This is a so let's talk about that.
Of course, yeah, it sounds pretty similar of what we do.
So maybe I have one.
Yeah.
This time to live, if I don't think about really stream data, but classical things, wouldn't it be easier to have something similar like the dependency graph, which means if I have pre-processed something, and then I have a dependency somewhere in my system between this source and my intermediate result, and someone just change it and get a notification. For non-stream data, that would be much easier than having to define the meaningful time.
Yeah, that's true. But of course, okay, if we leave out the non-streaming data, then couldn't the data be stale also?
Yeah. Maybe someone changed the database.
Yeah, exactly.
You change the database and then you get a notification. It makes no sense to have maybe not stale for 10 minutes or something. With stream data, you have a window, that's okay. But with real classical databases, it would be much easier to have a dependency and a notification. Something gets read, you're working on old data or something like that.
Yeah, that would be possible. For this kind of data, it would be possible. That's true. Yeah, that's something more easy, and also it's hard to define a fixed lifetime of data in seconds, for example. That's right. And in this way, we always know when to refresh the data or when something changes.
But this is only possible if you have invalidation-based cache.
Yeah. But at least if you have it, then you can use it. I have one critical question. You said this problem with the long-running operations, the real costly operations. I think, if I understood everything right, the basic idea of the entire work was to do, especially these costly operations during modeling time, to have the results ready when they are needed. And on the other hand, that's a real critical point, how to deal with that. You normally, when the modeler changes something, I think you have to stop it and you have to redo it. So if someone really works a little bit chaotic, it will not be of real help.
That's one issue we are currently facing. Yeah, that's true. And also, of course, if the modeler is not modeling the Mashup plan in a specific order, so if it doesn't start at the data sources, then we can't handle the partial execution also.
True.
Yeah.
If you think from the end result it goes backwards, then you have no chance.
Yeah.
More questions? No, then we thank you.